Hello students, I'm Miss Slate, and today we're going to be talking about molecular compounds. So molecular compounds are kind of the opposite or antithesis to ionic compounds, and they tend to have a lot of opposite properties. So while ionic compounds had very high melting and boiling points, molecular compounds tend to have low melting and boiling points. In fact, many molecular compounds are liquids or gases at room temperature. In fact, the molecular compound you're probably most familiar with is water, H2O. Also, unlike ionic compounds, molecular compounds will not conduct electricity when they're dissolved in water. And so we typically refer to them as non-electrolytes, meaning just non-conducting. Molecular compounds are also entirely composed of non-metal elements, so you will not find metals involved in molecular compounds. And they have a structure that we call the molecule, meaning, like as you see in these pictures over here, molecular compounds come in these discrete little bundles of bonded atoms instead of the interconnected crystal lattice of an ionic compound. And the reason they come in these discrete little bundles that we call molecules is because the way these compounds bond is very, very different. And we're going to talk about that in the context of water. So molecular compounds in general form when elements overlap their electron clouds and share valence electrons. So let's look at the example of water. So water, we know, is composed of hydrogen and oxygen. Hydrogen, as we know, has one valence electron, while oxygen, on the other hand, has 6 valence electrons. So when hydrogen and oxygen come together to form a molecular compound, they don't exchange their electrons. Instead, they're going to get close enough for their electron clouds to overlap. So we'll just draw, so imagine that there's, electron clouds, and they are going to come together and overlap their electron clouds and then share these electrons so that they can both have a full octet. So here we have oxygen again with its electron cloud. So what happens when water forms is that hydrogen atoms then come in, and the hydrogen atom overlaps its electron cloud with oxygen, and it shares its valence electron with oxygen. So hydrogen is sharing its one valence electron with oxygen, and oxygen is sharing one of its valence electrons with hydrogen. Now, hydrogen is a very, very small element. It's one of our exceptions to the rule of 8, and hydrogen actually has a full valence shell when it has 2 valence electrons. So hydrogen is in a stable arrangement. But you can see that oxygen is not yet. And this is part of why water is made up of 2 hydrogen atoms and 1 oxygen. Because oxygen needs to share valence electrons with actually 2 hydrogen atoms. So we'll have another hydrogen atom overlapping its electron cloud with oxygen and sharing this valence electron. So now we can see that both of these 2 hydrogen atoms have a full octet because hydrogen only needs 2, and oxygen has a full 8 valence electrons, so it is in its most stable arrangement as well. We can often represent arrangements like this with Lewis dot diagrams, but they're called Lewis structures instead. And in a Lewis structure, shared pairs of valence electrons can be represented with a line instead of dots. So the line represents two shared valence electrons between the elements. And that's how hydrogen and oxygen come together to form water. Now let's take a moment and talk about how we name molecular formulas. Luckily for us, it actually happens to be easier to write the names and formulas for molecular compounds than it is for ionic ones, because we simply use Greek prefixes to indicate the number of atoms of each element in the compound. And one thing that stays the same is you're still going to change the ending of the second element to IDE. So here are the Greek prefixes that are used when naming molecular compounds. 1 atom is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. You're not going to need to worry about prefixes greater than 10 for this class. Also, you are not going to need to memorize these prefixes. I will attach a list of these prefixes to any quizzes or assignments that require you to write the names and formulas for molecular compounds. The only other thing that you really need to make sure that you keep in mind is that the prefix mono is only used for the second element. So if you only have one of the first element in the compound, you don't use the prefix mono there. You only use it on the second one. And this is kind of a tricky thing to remember sometimes, so you might want to make sure that you star it or highlight it in your notes so that it stands out to you. Now, there are two exceptions to this naming convention. There are two compounds that have been used by humanity ubiquitously for a very long time, and so they only are referred to by their common names. The first one is ammonia, NH3. No one calls it nitrogen trihydride. It's just ammonia. So that one you are going to have to memorize, start in your, so that one you are going to need to know that NH3 is actually ammonia. So again, you're probably going to want to star this in your notes or highlight it so it stands out. The other compound that only goes by its common name should be really familiar to you, and that's H2O, or water. No one calls it dihydrogen monoxide. It's kind of silly. It's just water. Even scientists will only refer to H2O as water. Now let's do some example problems so that you guys can kind of get a better handle on how the naming is going to work. So our first example is N2O5. Well, first off, you'd want to look at your list of prefixes. The Greek prefix for 2 is di, so I'd start with di. Then you need to determine what element N is. It's nitrogen. If you didn't know that, though, you could check your periodic table. Additionally, if you don't know how to spell nitrogen, look on the periodic table. It'll be spelled correctly there for you. So it's going to be dinitrogen. Is the first part. Then we have to look at the next element in the compound. It's O5. Well, I'm going to need to use the prefix for 5, which is penta. And then O is oxygen. But we're going to need to change the ending to IDE, just like we did with ionic compounds. So it's going to be dinitrogen pentoxide. Our next example is CO. Well, there's no little number, no subscript after C, so we know there's only one of them, but the prefix mono is only used on the second element, so we can just write the element C's name, which is carbon. Again, if you didn't know what element it is, check your periodic table. So we have carbon. Then we have the element O, oxygen. Again, we're going to need to change the ending to IDE and make it oxide, but also notice there's no subscript after oxygen, no little number. That tells us that there's only one oxygen atom present. And oxygen is the second element, so we are going to need to use the prefix mono. So it becomes carbon monoxide. So CO is carbon monoxide. Our next two examples, we've got to go the other direction. So we're given the name carbon tetrachloride, and now we have to write the chemical formula for it. Well, carbon has no prefix in front of it, so that tells us that there is only one carbon atom. So I'm just going to write a C with no subscript, because you never need to write a subscript of 1. Then our next element is chloride. Chloride is coming from chlorine, which has the symbol Cl. Again, if you weren't sure what the symbol for a particular element is, check your periodic table. The prefix on chloride is tetra. So tetra is the prefix for 4, so I need to put a subscript of 4 after Cl in my formula. So carbon tetrachloride is CCl4. Our next example is phosphorus, triphosphorus dibromide. Well, phosphorus is the first element. Phosphorus has the symbol of P. It has the prefix tri. Tri is the prefix for 3, so I'd make it P3. And then our second one is dibromide. So bromide, that's coming from the element bromine, which has the symbol R. And the prefix is di. Di is the prefix for 2, so I'm going to put a subscript 2. So triphosphorus dibromide is P3Br2. And so really, as long as you have your list of Greek prefixes and what prefix goes with what number, you should be able to write the names and formulas for molecular compounds. That wraps up our lesson for today. I hope you guys have a great day, and I'll catch you next time.